Welcome back, students. In this part of the lecture, we'll see NFA, which stands for Non Deterministic Finite Automaton. It is similar to the DFA and is a 5-tuple set. 5-tuple set and is equal to DFA by power. That is, the NFA can be converted into the equivalent DFA, or for every NFA there is equivalent DFA available or can be designed. In the 5 tuples of this NFA, which is, let's say, this is a tuple number 1, second tuple, third tuple, fourth and fifth tuple. It's a 5 tuple sets in which 4 tuples, that is Q, which is non-empty set of states, it's a finite set. The second tuple, sigma, which is the input alphabet. Third tuple, initial state. And the fourth tuple, which is the non-empty set of final states, are similar to the DFA. So the tuples which are similar to the DFA are Q, sigma, Q0 and F. So I'm repeating, Q is the non-empty set of states, finite set of states. Sigma is the input alphabet. Q0 is the initial state that belongs to the Q. And F is the non-empty finite set of final states. F must be subset of Q. All these are already discussed in the previous lectures. Here in case of NFA, the transition function, that is sigma delta, is different from the transition function of DFA. In case of the transition function of DFA, it can be defined as Q cross the input alphabet to the Q. But in case of the NFA, this is the transition function of DFA. But in case of NFA, the transition function is defined as Q cross sigma to 2 raised to power Q. Here 2 raised to power Q is a power set of Q. Power set of Q. That is set of all subsets. So here in case of NFA and DFA, the transition function is different. Say, for example, let's explain the transition function of NFA, which is Q cross input alphabet to 2 raised to power Q, where 2 raised to power Q is power set of Q. For example, if the set of states in this NFA are A and B, then the power set, which is set of all subsets including the empty set and the set itself, would be the empty set would be the 5, empty set, A itself, B, and then AB. It implies that for a particular state, let's say A, and a particular input, for example A, the machine can have transition to empty set 5, that is the transition is not defined, or the machine can go to the state A after transition, or it can go to the state B according to this power set, or it can go to the state A and B both. So in case of the transition function of NFA, for a particular state and a particular input, the transition may go to nowhere, that is, it is not defined, or it can go to more than one states. Let's see it with the help of example. So for example, we have two states, let's say state number A, and this is the second state, which is the state B. A is the initial state, whereas B is the final state. So for example, on input A, it is going to B, and this is on input B, the state B on input B is going to itself. In case of the state A, for the particular input A, it is going to be, but the input B is not defined here. So if we prepare the transition table of this NFA, then we'll see that, for example, here we have two states, A and B. A is the initial state, whereas B is the final state. And we have two input symbols, A and B. So the state A on input A is going to B, but the input B is not defined, which is possible here in case of the NFA. That is, it is going to nowhere. Therefore, we have phi here. Similarly, B on input A is going to nowhere. That is, it is not defined here. Therefore, we will have phi here in the transition table. State is B and the input is A, which is not defined. That is, it is clear in the diagram. It is not given. It is not defined. Therefore, we have phi here. B on input B is going to itself. This is a transition table for this given NFA. Let's take for a particular NFA how the input string is processed. So for example, we have this NFA given and we have to process the string W, that is A, B, whether this input string is accepted by this automaton or not. Here in this NFA, the initial state is A and the final states are B and C. So B is the final state and C also is the finite state. The input symbol that is given here are A, comma B. So in order to process this input string AB, we have to use extended transition function. Here the initial state is A and the input string is AB. If we extend this transition function, then we will have A and we will take the first input symbol and this is the remaining input string. So A on input A is going to B, therefore we will have B here and this is the remaining input. If we extend the transition inside, we will have, and this is the remaining input epsilon. So the state on input B is going to nowhere, therefore we will have phi here. And applying epsilon on phi will have or will result in the phi itself. So as a processing of this input string, we are reaching to the phi, which is not a final state. Therefore, the input string AB is rejected, as phi does not belongs to the final state F. Therefore, this input string is rejected. Let's take another string for the same NFA, and let's say at this time the string is AA. A is the initial state and input string that we are testing is the AA. Extending the function, we will have the first input symbol and this is the remaining input symbol. So A on input A is going to the state B. Therefore, we will have B and the remaining input A. If we extend the transition function again, then you will have BA, and this is the remaining input, which is epsilon, that is nothing. So B on input A is going to C. So here you will have C and the remaining input epsilon. From the property of the transition function, it is clear that the outcome of this transition would be the C itself. As C belongs to final state F, or C is the final state, therefore this input string is accepted. Let's take one more example. Let's say this is the example number 2, in which we have given this NFA, and we have to check that the input string A, B is accepted or rejected. A is the initial state and the input string that we want to process is AB. If we extend the transition function, then we will have and the first input symbol, and this is the remaining input. From the diagram, state transition diagram, it is clear that the state A on input A is going to two different states, which is A itself and B. Therefore, as a transition of A on input A, we will have the state A and B. This is the remaining input symbol, which is small b. If you extend this transition function inside, where you have two states A and B, and the input symbol is B, what we will do, we will take the first state and the input symbol B, and then we will find the union of second transition. The state is B and the input symbol is small b. A on small b is going to be itself, that is this one, and B on B is not defined. Therefore, we will have phi here. I'm repeating, A on small b is going to the state B, whereas the state B on input B is going to nowhere. Therefore, we'll have the phi here. The outcome of this transition is B, and the union phi is B itself, and the remaining input is epsilon. That is, both A and B are consumed process. Now we are left with the epsilon. From the property of the transition function, we know that the outcome of this transition would be the B itself. As B belongs to the final state, therefore this input string is accepted by this NFA. Hope this example is clear to you. If you have any question, please do write in the comment box. Thank you very much. We'll see you in the next lecture. Till then, thank you very much.